Hello everyone, welcome to Civil Galaxy. Myself Dr. Pruthviraj B S. In today's session we shall solve one continuous beam where support B is sinking by 10 millimeters with the help of Kanis method, and the value of E they have given, which is 2.1 into 10 raised to the power of 5 Newton per millimeter square. This value I have converted in terms of kilonewton per meter square, which will be 2.1 into 10 raised to the power of 8 kilonewton per meter square, and the value of I they have provided, which is 85 into 10 raised to the power of 5 millimeter to the power of 4, and converting this in terms of meter to the power of 4, we are having a value of 85 into 10 raised to the power of minus 7 meter to the power of 4, and the value of delta which is sinking, which is in the question they have given, that is 10 millimeter. So converting this in terms of meter will be equal to 0.01 meter, and if you want the value of EI, which is the product of E, this value, and I, which will be equal to 1785 kilonewton meter square. So from our previous classes we know the first step for the Kanis method is to calculate the fixed end moments. To calculate the fixed end moments. See, if we consider the span AB here to find out the fixed end moment, support B is having a sinking of 10 millimeters. So this sinking of support, the effect also needs to be considered at this stage itself, where we are finding out the fixed end moment. So for that, if we consider the span AB over here, this is A and this is point B, which is having a sink over here, which is given as delta is equal to 10 millimeters. So here, which is in the anti-clockwise direction, here it is anti-clockwise direction. So here, if we are considering the effect of sinking, we know the formula, which will be equal to 6EI delta upon L square. Since it is anti-clockwise negative here from B to A, so we have to consider the sinking of supports, the value which is 6A delta upon L square as negative. So finding out the fixed end moment from span A to B over here, fixed end moment from A to B. See here, if you see the span AB, which is carrying an eccentric loading of 8 kilonewton at a distance of 2 meters from point A or support A, the formula we know, which will be equal to minus WA B square upon L square. So since we are taking the consideration of sinking of support also here, which will be equal to minus 6 EI delta upon L square. So now putting the values over here, minus the value of W here is 8 kilonewton, A, that is this distance, which is 2 meters, into 3 square upon that L square. The span here is 5 square minus 6, the value of EI we have got here, which is 1785. So multiplied by 1785 into delta, the value of delta we have considered here in terms of meter, which is 0.01 upon L square. The total span here is again 5 square. So just computing these values, which will be equal to, so this value is minus 5.76 minus this value will be equal to 4.284. So fixed moment from A to B will be equal to, so fixed moment from A to B will be equal to minus 10.044 kilonewton meters. So this is the value for fixed end moment from point A to B. Now if we need to find out the fixed moment from B to A, so here I will write over here. So fixed moment from B to A So now everything remains same, only the sign about the fixed moment from B to A changes, because here we are coming from left to right. Now fixed moment from B to A going from right to left, we know it is positive, so it will be plus W A square B upon L square, the formula whenever we are having an eccentric loading, minus the effect of sinking, that is 6 EI delta upon L square, which will be equal to the value of W, that is 8 into 2 square into 3 upon the total span is 5 square, minus 6 into the value of EI we have taken here, which is 1785 into the value of delta is 0.01 meters upon the total span, which is 5. So 5 square. So fixed moment from point B to A, which will be equal to, so this value here will be equal to 3.84, and this value will be minus 4.284. So the fixed moment from point B to A, here we are having a value of minus 0.444 kilonewton meters. So now similarly we need to find out the fixed end moment for another two spans, that is B to C and C to B, similarly from C to D and D to C. So the next fixed end moment will be, see here, that is fixed end moment from B to C, which will be equal to, see here, from B to C for this span. So if we consider this span over here, just I will just a minute. See here. So if I want to consider the fixed moment from B to C over here, that is, this is the beam. So this is point C and this is point B. At B we are having a support which is sinking upon by 10 millimeters. So if you want to find out the fixed end moment from point B to C, since it is having an eccentric loading over here, we know the formula, which is minus W A B square upon L square. So here, as we are taking the sinking of support into consideration, here the value is positive here. So the value, that is 6 EI delta upon L square, should be considered as positive over here. So it will be plus 6 EI delta upon L square. So now taking the values, W here they have given, which is minus 5. So this is the distance from point B for A, that is 5 into 3 square upon the total span here is 7 square, plus 6 EI value we have known, we have considered here, which is 1785 into delta is 0.01 meters upon the total span, which is L square. So now this value will be equal to, this value comes out to be minus 3.673 plus, so this value will be 2.186. So adding these two values, the fixed end moment from B to C will be equal to minus 1.487 kilonewton meters. So similarly, if we want to find out the fixed end moment from C to B, I will consider here fixed end moment from C to B, which will be equal to, if you are coming from right to left, the value will be negative, and for eccentric loading, the formula will be plus W A square B upon L square plus the effect of sinking here at point B, which will be 6 EI delta upon L square. So here W value, that is at this point, which is plus 5, and the distance A is 4. So 4 square into 3 upon 7 square, and this value 6 into EI value will be 1785 into delta value 0.01 upon L square. So here we are having a value of, this value will be equal to 4.898 plus this value, which is 2.186. So fixed moment from point C to B will be equal to 7.084 kilonewton meters. So this is the value for fixed end moment from point C to B. Now we need to find out the fixed end moment for this span, that is CD. So see here. So considering the fixed end moment here about this point for C to D. See, if you observe the portion here C to D, the effect of sinking is only about the point B here. So for span CDs, there is no effect of sinking. So we need not consider the effect of sinking for the span CD over here. So to find out the fixed moment from point C to B, since it is having an UDL, the formula we know here directly, that is W L square upon 12. Since here it is coming, we are coming from left to right, the value is negative over here. So here the span they have given, which is 8 meters. So here the value we can take directly here, which is minus W here is 1, and the total span here is 8 square upon 12. So fixed moment from point C to B will be equal to minus 5.33 kilonewton meters. Similarly, for fixed moment from point D to C, the value or the formula remains same, only the sign changes, that is WL square upon 12, which will be equal to 1 into the span here is 8 square upon 12. So fixed moment from point D to C will be plus 5.33 kilonewton meters. So this is the value. So if you observe here, the support A and support D are simple in nature. So we need to go for a modification of fixed end moments, so that the final end moments about point A and point D will be equal to 0. So here the step 2 will be modification of fixed end moment. See here, at support A we are having a simple support, and the fixed end moment from point A to B we have got a value of, which is minus 10.044. So since we are having a fixed moment from point A to B, the value is minus 10.044. Now we have to take or consider an additional moment into consideration, such as the final end moment about this point A, which is a simple support, will be equal to 0. So for that I can consider an equal and opposite moment, which is an additional moment, which is plus 10.044. So now this value will be equal to 0. So from moment distribution method, we know that whatever the additional moment we have considered, half of that value needs to be carried to the other end of the same member. So the fixed end moment from point B to A, we know we have the value which is minus 0.444. This is the fixed end moment from point B to A, plus half the value of the additional moment whatever we have considered here, so which is 10.044. So this value will be equal to 4.758 kilonewton meters. Similarly, at support D, we are having a simple support. So the final end moment about this point will be equal to 0. So here if we modify the value, that is the fixed end moment from D to C, which we have got a value over here. This is plus 5.33. So the final end moment, if the value should be 0 here, we have to take an equivalent opposite additional moment, which will make the value to be 0. And whatever the additional moment we have considered here, half of that value needs to be carried to the other end of the same member. So the fixed end moment from point C to B will be equal to, from C to D we are having a value of minus 5.33 plus half the value, that is additional moment whatever we have considered, which is minus 5.33. So the value will be here equal to minus 7.999 kilonewton meters. This is the modified fixed end moment from point C to D. So these values we need to consider whenever we are calculating the final end moments. So here the next step will be to calculate the stiffness and rotation factor, which is represented by U. So for that I have considered a table over here, where we will consider the joint and the members for that particular joint, and for that particular member we shall find out the relative stiffness, and we shall take the consideration of the total stiffness for that particular joint, and we shall consider the rotation factor for each member, which is given by U is equal to half into K by sigma K. So if you observe here, we are having two joints over here, where this joint B is connected to two members, that is from B to A and from B to C. So we are having B to A and B to C. So now if you want to find out the stiffness for this particular member, I have to consider the far end conditions. So here if I consider the far end conditions, here B is the near end and A is the far end. So since B is the near end, A is the far end here, and as the support A here is simple in nature, so we know whenever we are having a support other than the fixed support, the stiffness will be equal to 3 upon 4 into I by L. So here we are having a value 3 by 4 into I upon the total length here is 5 meters, which will be equal to, here I'll write, which will be equal to 0.15 I. So for member BC here now, if I consider B is the near end and C is the far end over here, since C is an intermediate support, and in structural analysis, even the intermediate support we consider it as an fixed support. So for fixed support, the stiffness value will be equal to I upon L, which will be equal to, so I value remains I upon the total length here is 7, which will be equal to, so I upon 7, which gives a value of 0.142 I. So now taking the summation of these two value for joint B, we are having a summation of value 0.292. So this is the value here. Now if I take the joint C over here, C is connecting to the member, C is connecting to the member from C to B and from C to D. So if I take this from C to B here, C is the near end and B is the far end, and B is an intermediate support. We know that for intermediate support we are taking it as an fixed support. The value will be I by L, which will be equal to I upon 7, which is 0.142 I. And for C to D, C is the near end and D is the far end. Since D is a simple support over here, the stiffness value will be equal to 3 upon 4 into I by L. Any other support, then the fixed support, maybe it is a simple support, roller support or a hinge support, we are taking only the 75% of the value, and if it is a fixed support, we are considering the 100% of the value, which will be equal to here the value 3 by 4 into I upon the total length here is 8 meter, which will be equal to 0.094 I. So now the summation of these two value will be equal to 0.236. So now if you want to find out the rotation contribution here, just applying the value here, minus half into K we have got here, that is for member BA 0.15 I and sigma K is 0.292. So if we put the values over here, for member BA, U value we are having minus 0.256, and for span BC we are having a value of minus 0.244. So now for CB value we are having rotation factor as minus 0.302, and for CD it is minus 0.198. So these are the values for the rotation factor for member BA, BC, CB and CD. So here the fourth step will be to calculate the rotation contributions, that is through the iteration process. So for that I have considered a table over here, which is also called as a Kanis table. So in this Kanis table, let us represent the fixed end moment whatever we have got in the first step. So fixed end moment from A to B we have got, that is 0, because we have got the modification fixed end moment, that value we need to consider over here. And the modified fixed end moment value from B to C we have got, which is plus 5.78, and from B to C the value we have got minus 1.487, and the modified value from C to B we have got, which is 7.084, and the modified value from C to D is minus 7.999, and D to C is 0. So inside this box we have to consider, see here, first of all, the rotation contribution in Kanis method is only calculated at the intermediate supports and not at the end supports. So these intermediate supports I have just replaced it with the boxes, which is also called as Kanis boxes. So inside this box we have to write the summation of these two values over here, that is fixed moment from B to A and fixed moment from B to C. So the summation of these two values I have to write in this box over here, which will be plus 3.091, and here the summation of these two values will be minus 0.915. And inside this value over here, I have to consider the rotation contributions, whatever we have calculated in the step 3. So here the rotation contribution for the member B to A, we have got a value of minus 0.256, and from B to C we have got a value of minus 0.244, and rotation factor for C to B, the value is minus 0.302, and from C to D the value is minus 0.198. So now we have to consider the rotation contribution. As I told, we are calculating only for the intermediate supports. So if I want to calculate the rotation contribution, which is represented by M dash AB, and here it will be M dash BA, here will be M dash BC, M dash CB, here it is M dash CD and M dash DC. And already, as I have told, the rotation contributions for the end supports will be equal to 0 over here, since we are calculating only for the intermediate supports. And now if you want to find out the rotation contribution, we know the formula, which will be U multiplied U into summation of fixed end moment plus summation of far end rotation contributions. This is a formula we have to use to find out the rotation contributions about that particular point. So now if I consider moment about, M dash BA to find out the rotation contribution, I know the value of U here, I have to consider this value here. So, which is minus 0.256 into summation of fixed end moment we have calculated here, which is plus 3.091 plus far end rotation contributions. See here for point B here, the far end rotation contribution here, this one, that is M dash AB. So this value I have to consider. Similarly, if I come for this side, this is the far end rotation contribution. So I have to consider the value of M dash CB over here. So for point C, M dash BC will be the far end rotation contribution, and here M dash DC will be the far end rotation contribution. So the far end rotation contribution, if you take here for M dash BA, here it is 0 plus the far end rotation contribution M dash CB, we don't know, we have to calculate. So the first iteration process or the iteration cycle will be equal to 0, which will be having a value of minus 0.862 kilonewton meters. So this value will write here, that is minus 0.862. So this value will consider here. Next, it is M dash BC. So the value of U here is how much? Minus 0.244, and the other value remains same, that is plus 3.091, which is summation of fixed end moment plus summation of far end rotation contribution here, how much? 0 plus the value of M dash CB here, this is 0. So the value will be equal to minus 0.822 kilonewton meters. So this value we have to write here, which is minus 0.822 kilonewton meter. I am writing only the values and not the units over here. Next, we need to find out the rotation contribution for C to B, which will be equal to, the formula we know U, the value of U here is minus 0.302 summation of fixed end moment. So the summation of fixed end moment here is how much? Minus 0.915 plus the value or the summation of far end rotation contribution. So the value of far end rotation contribution here we have got, which is a new iteration value, which is minus 0.822 plus the far end rotation contribution here about this value is 0. So we are having a value of here, which will be equal to 0.276 kilonewton meters. So this value we need to write here, that is plus 0.276. So next we need to find out the rotation contribution for C to D. So everything remains same. Sorry. Here the value of U will be this one, minus 0.198, and the other values remains same, that is summation of fixed end moment is minus 0.915, this value, minus the new iteration value we have got here, far end rotation contribution, which is minus 0.822 plus 0 will be equal to 0.181 kilonewton meters. So this value we have to write here, plus 0.181. So here we need to carry out the iteration process until we are getting the similar values over here. Say for example, this was the first cycle. We have to go on carrying the iteration process such that the values will be similar over here. So now if I take this as cycle 2 or the second iteration process, everything remains same, only the far end rotation contributions changes here. See here, u remains same and the summation of fixed end moment remains the same, only the summation of far end rotation contribution changes. So here plus the far end rotation contribution here will be 0 plus the far end rotation contribution here. Now we have got a value, a new iteration value, which is plus 0.276, which will be equal to minus 0.926 kilonewton meter. So this value will write here 0.926. So next will be plus 0 plus 0.276, which we are having a value of minus 0.882 kilonewton meters. So minus 0.882 kilonewton meters, this value here. So if we come for m dash cb, here everything remains same, only the far end rotation contribution keeps on changing. So here u value we know, which is minus 0.302. The summation of fixed end moment we know, which is minus 0.915, and the summation of far end rotation contribution here we have got a new value, which is minus 0.882 plus the summation of far end rotation contribution over here is 0 at this point. So which will be equal to plus 0.525. So this value we will consider here, plus 0.525, this value. So here will be 0.882 plus 0, which will be equal to 0.344 kilonewton meters. Here also kilonewton meters. So here it will be plus 0.344. So if we observe over here, the values are not similar. So we need to keep on continuing the iteration process. So here we will consider the third cycle. Here everything remains same, only this value keeps on changing. Here now this far end rotation contribution will be 0 over here for both, plus the far end rotation contribution here, which is 0.525, a new iteration value, which will be equal to minus 0.930 kilonewton meter. So here minus 0.930 kilonewton meters. So here also 0.525, which will be equal to minus 0.887 kilonewton meter. So we shall write here minus 0.887. So here in this we are having a value, which is the summation of far end rotation contribution here is how much? A new value of iteration value here, this value minus 0.887 plus 0, which will be equal to 0.543. So this value will write here plus 0.543 kilonewton meters, and here will be minus 0.887 plus 0, which will be equal to plus 0.356 kilonewton meters. So this value will write here, which is plus 0.356. So we can observe over here almost the values are similar in each. The value of rotation contribution is almost similar. So we shall see one more cycle, maybe we will get the similar values. So if we are considering the next cycle, cycle 4. So here for m dash BA, the value far end rotation contribution will be 0 plus here this value, which is 0.543, which will be equal to minus 0.930 kilonewton meters. So here it is minus 0.930. So now the values are similar here at m dash BA. Similarly, plus 0.543, here it will be minus 0.887 kilonewton meters. So here it is minus 0.887. Sorry. And here a new iteration value, that is summation of far end rotation contribution, here is how much? Minus 0.887 plus 0, this value here. So will be equal to 0.543 kilonewton meter. So here it is 0.543. Similarly, for m dash CD will be minus 0.887 plus 0 will be equal to plus 0.356 kilonewton meter. So this value we have to write here 356. So now if we observe over here, the values are similar in comparison with the third cycle. So here we can now stop the iteration process. See here about this point here. So this we can consider the value as the rotation contributions for each. So here the final step will be, there is a last step will be to find out or to calculate the final end moments. So if we need to calculate the final end moment from point A to B, since we know the point A is a simple support over here, in the second step we have done the modification of fixed end moment. So the final end moment for A was 0. So this value from A to B will be equal to 0. Now the final end moment from B to A, where we are having the formula, which is fixed end moment from B to A plus 2 times the rotation contribution about the near end plus 1 times rotation contribution about the far end. So here we know the value. In the step 2 we have considered the modified fixed end value, which will be equal to the modified fixed end moment value here we have got is plus 4.758 plus 2 times rotation contribution, here this value m dash BA, which is minus 0.930 plus this value is 0 here because m dash AB is 0. So the final end moment for point B to A we have got plus 2.718 kilonewton meters. Now we have to calculate the final end moment for B to C. So fixed end moment from B to C plus 2 times the rotation contribution about the near end plus rotation contribution about the far end. So the fixed end moment from B to C, the fixed end moment from B to C, if you see here, we are having a value of how much? Minus 1.487 plus 2 times the rotation contribution about the near end, that is minus 0.887, that is m dash BC. So m dash BC value we have got here is minus 0.887 plus the rotation contribution about the far end. So m dash CB. So m dash CB we have got here is plus 0.543. So the final end moment for point B to C value we are having is minus 2.718 kilonewton meters. So we can observe here at point B, from B to A it is plus 2.718. So from B to C it is minus 2.718. That means the calculation is correct because we are having an equal and opposite moment. Similarly, for the, here I'll write moment from now B to C, this will be C to B, that is fixed end moment from C to B plus 2 times the rotation contribution about the near end plus 1 times rotation contribution about the far end. Here M dash CB, M dash CB, how much we have got here? This one. Fixed end moment from C to B, that is 7.084 plus 2 times the rotation contribution M dash CB. M dash CB value we have got here, that is plus 0.543 plus M dash BC. So M dash BC value, how much we have got here? It is minus 0.887. That is the far end rotation contribution, that is minus 0.887. So this value, that is final end moment from C to B value, will be equal to plus 7.285 kilonewton meters. So now final end moment from C to D. So here fixed end moment from C to D plus 2 times rotation contribution about the near end plus 1 times rotation contribution about the far end. So here fixed end moment from C to D, the value we have got, which is minus 0.7999 plus 2 times rotation contribution M dash CD. Here we have got the value, that is 0.356 plus this value is 0 because M dash DC here is 0. So the final end moment from C to D is minus 7.285 kilonewton meters. So here also we can observe here at point C over here, from C to B it is plus 7.285 and from C to D it is minus 7.285, which is equal and opposite in moment. So the calculation is correct. So lastly, from D to C it is 0 because it is an end support, and the end support here is simple in nature. In the modification of fixed end moment, in the second step only we have calculated the final end moment for point D to C. So using these values now we can draw or we can plot here in this beam over here, that is at point A it is 0 over here, from A to B it is 0, from D to C it is 0 over here. Now from B to A we are having a clockwise rotation here, which is 2.718 kilonewton meter. Here it is negative 2.718 kilonewton meter from B to C. Here we have calculated. So from C to B is positive, having a value of 7.28. Here it is negative minus 7.285. So here it is 7.285 kilonewton meters. So here this value is 0. So using these values, further we can calculate the support reactions and the maximum bending moment for this particular problem. Similarly, we shall see some more problems related to Kanis method in the next coming classes. Thank you.